don't take him seriously.
I'm not going to.
That wasn't needed. That wasn't needed.
But you don't like when we're late.
I don't like it when you're late.
Wow. Is that your low blow of the day?
No, that's only medium.
Mm. Oh, that makes me want to cry.
I got tissue.
You are prepared.
He was ready, he knew this was coming.
Made it his goal.
Well, you cut the legs out of Tony at 4:30 today, though. You cut Tony's legs right off.
You have an admirer.
No, it's not an admirer, it's a hitman. So bye, guys, I'm gone. Okay, do me in, sir.
Bye, Tom.
Man, that access is kicking my butt.
Good. Wow, success story. What are you doing
Access is
between 2 and 4
awful.
tomorrow? Oh, Saturday, you're too far away. Well, you want to spend some time together?
You know,
You gonna stay with it?
yeah, I'm gonna keep plugging at it, but
That's how it's done.
my query, drop the tables down in the box, hit the run, but none of the information comes up.
Oh, is there any information that should come up? Check your tables.
Yeah, I put the information.
Are
in
you
there.
sure that there is information that matches your query? That's what happens to me, I get at the output. Because the query is doing what you told it to do,
Yeah,
unfortunately.
Last name, and there's last
Yeah.
name there, I put the size, the item name.
Right, but unfortunately, what you
Nothing
told
comes
it to do might not be what you thought you told it to do.
Exactly, in its language.
That's usually
I don't
where the
understand
drop
its
difference is. Been there and cried myself.
And then the other thing, I had to check, 2010 is the latest version, we don't have anything different that you're using.
Not around Maryland, no.
So, in the composite, like last night, when we pulled the primary keys down and dropped it into the composite table, you know, we took the keys to relationship, and build a relationship.
Yes.
You drag the key from
Right.
one table and drop it in the composite table.
Right.
And those keys showed up in the table on the screen,
Mm-hmm.
but they won't show up in my box,
Both are.
the composite table.
Okay, I'm gonna have to look at that,
Yeah.
sit down.
But it builds the relationship.
Yeah,
But the key, like in what we saw last night, the key with the name of the table doesn't show up in the box.
I'd have to look at that to see it.
No rush, I'm still kicking.
Okay.
Thank you.
Pleasure. Hi. Tough assignment. Okay, so we're going to give a little slack to our latecomers and extend the break. This stays in this room.
Not for me, though.
Stephanie has a child alert. And I have no idea what Freddie's doing. Might be jumping off the
Kids at the pool.
second floor. Okay. But we sort of have to ease our way back in, and so we'll be working in our textbook, page 233. Is somebody running? Move Freddie's table up, give him the case studies on the others.
Oh, it'll be funny.
Think so?
A little bit.
He'll probably be all about being like,
You're so mean.
Hey, I've known Freddie for almost a decade, so we can blame this on me, and it'll be funny.
Well, he might not come back, I mean.
Oh, I can't come in? All right, bye. I'll come back tomorrow.
Okay.
Freddie's house keys
Okay,
are in
we
that
will have
bag.
to start. Okay, so we're going to talk about a unique type of discrete probability distribution. One type of many. And this particular type is called the binomial. The binomial discrete probability distribution. It's a particular type of a probability distribution. Now, you know a probability distribution is signaturized by having an x parameter that can take certain values. And each one of those values has associated with it a probability of occurrence, and the sum of the probabilities add up to 1. This is the definition of a discrete probability distribution.
How bad would you feel if you would have like broke his nose? Like, that would have been terrible. It was all his fault.
Hannah said to do it. Hannah said to do it.
It was funny.
That's why you're laughing. That's the worst joke I
Because
could.
she couldn't get out earlier because I had to block.
Yeah, we all saw that, we all saw that. We all saw that. Okay, so the subject of chapter 5 is discrete probability distributions. A discrete probability distribution means that we have a variable x that can assume certain discrete variables, values, and each one of those values has a probability of occurrence associated with it, and the sum of those probabilities add up to 1. Now we're going to look at a special type of discrete probability distribution known as a binomial probability distribution. And I'm going to lead it into you by an example. Background. We need to know something about the background population. Misawa Air Base, smokers, 30%. Non-smokers, 70%. So you have to know this going in. You have to know the percentages in the background population. This is the first requirement for a binomial distribution. You know the percentages in the background population. I'm going to assume there's 30% smokers at Misawa Air Base and 70% non-smokers. Now, I'm going to select okay, so C10-2 is 45, too many. C6-2, 15, too many. C5-2 is 10, right. I'm going to select 5 individuals at Misawa Air Base random, and I'm going to give them names, A, B, C, and D. An E. A, B. So there are 5 labeled individuals, A, B, C, and D. That's their names. Now, what I want to know is, what's the probability that amongst my 5, I will find exactly 2 smokers? What's my probability that amongst my 5 selectors, I will find exactly 2 smokers? Okay, now, the probability calculation that we're going to use is that the probability of A times B times C times D times E, or just the probability of 2 things, A and B, is the probability of A times the probability of B, agreed? So now the probability of A smoking is what percent?
30%.
0.3. The probability of B smoking is what? 0.3. Now I've stipulated that I will have exactly 2 smokers. So that means that C, D, and E have to be non-smokers. So what's the probability that C is a non-smoker? So if I multiply 0.3 times 0.3 times .7 times .7 times .7, I have found the probability that A smokes, B smokes, and C, D, and E do not smoke, agreed? But, all I'm caring about is that if I have exactly 2 smokers, agreed? I don't care if it's A and B, or anybody else. So now let's have A smoke, and C smoke, and B doesn't smoke, and D doesn't smoke, and E doesn't smoke, agreed? That's another possibility that fits my stipulation, that I have exactly 2 smokers. Now, what's another one that I can have is, A, B, C, or D, or E. I could have this guy smoke, and I can have D smoke, and the others not smoke, agreed? Or I can have A, B, C, D, and E, and I can have A smoke and E smoke, but these don't smoke. Now let's continue with possibilities. I can have A, B, C, and D, and E, and I can have this one smoke and this one smoke. Let's continue. A, B, C, D, and E. I can have this one smoke and this one smoke. A, B, C, D, and E. I can have this one smoke, this one smoke. A, B, C, D, and E. And I can have this one smoke, this one smoke. A, B, C, D, and E. Now this one smoke, this one smoke. A, B, this is the last one. This one smoke and this one smoke. Now those are the only findings that satisfy my stipulation that I have exactly 2 smokers and 3 non-smokers, true? So notice, the probability of this and this and this and this and this is the probability of this times the probability of this times the probability of that times the probability of that. Because what's the probability of getting one ace followed by the probability of another ace? 4 over 52 times 4 over 52, agreed? What's the probability of 3 aces in a row? 4 over 52 times 4 over 52 times 4 over 52, 4 over 52. So now what's the probability of 2 aces followed by 3 non-aces? And this is with replacement. So what's the probability of the first ace? 4 over 52. The probability of the second ace? Now the probability of not an ace. 48 over 52? 48 over 52? 48 over, now this is the same calculation as this. What's the probability of a smoker followed by a smoker, followed by a not smoker, not smoker, not smoker? So we have to multiply those numbers together. And we'll find the probability of getting that occurrence. So what does it come out to be?
0.0308.
0.03. Now, I'm going to make life easy. If I calculate the probability of any other occurrence, will it not be exactly the same?
Yes.
So if I call the probability of a smoker P, and I call the probability of a non-smoker Q, then what I have here is it not P squared Q cubed? What do I have here? P squared 2Q cubed, agreed? What I have here is P squared Q cubed. All of them, agreed? But my request is satisfied if any one of them occurs. If any one of them occurs, I found success, agreed? So if I take a deck of cards, what's the probability of pulling a 6 or an 8 out of the deck of cards?
8 over 52.
Right, because it's the probability of pulling a 6 plus the probability of pulling an 8, agreed? Because both yield success. What's the probability of pulling a 6, an 8, a 9, or a 10? 4 over 52 plus 4 over 52 plus 4 over 52, agreed? Now, what's the probability of getting this, or this, or this, or this, or this, the probability of this, plus 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 the probability of that, agreed? Now, how many strings do I have? 10, agreed? Count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that is all possibilities. Now, there's a very easy way that you could have found 10. And it is as follows. I have a group of 5, agreed? And in that group of 5, I want to find 2 smokers. So how many groups of 2 can you find from a pool of 5? Is it not C52? So calculate, what's C52? 10. And we've spelled them out in detail. So the probability of getting exactly 2 smokers is equal to the number of different ways you could insert the 2 smokers into your group of 5. That's C52 times the probability of each group occurring, which is P2Q cubed. Agreed? Now we're going to make some new notation. N equals the size of the group. In this case, it's 5, agreed? So, and X equals the number of successes. In this case, 2 smokers. So in generalized notation, the probability of finding X is equal to the number of ways you can find X in a pool of N times the probability of getting X successes, which is P to the X, followed by Q failures, which is 3. Where did the 3 come from? It was 5 minus 2, agreed? Or N minus X. So this is the general formula that will tell you what is the probability of finding X successes in a group of N size, when you know that the background probability is P. And this calculation, this entire distribution, because X can have all values, is known as a binomial distribution. Now, that was a rough lead-in. Now we're going to take it a little more closely, okay? So let's go to 233. The yellow box at the bottom. A binomial probability distribution results from a procedure. Our procedure here was to query 5 smokers. To query 5 smokers, agreed? The procedure has a fixed number of trials. How many smokers did we choose? 5. So that's our fixed number of trials, agreed? We could have chosen 10 smokers, 20 smokers, or 3 smokers. But that number is fixed, agreed? Now, the trials must be independent. And that is, does the probability that Bill smokes become affected by the probability that Alice smokes? Let's say ideally not, agreed? So the result, the probability of any particular person smoking is independent of what all the others are doing, agreed? So that means each one of these is an independent result. Each trial must have all outcomes classified into only 2 failures, commonly referred to as success and failure. These are 2 outcomes. They either smoke or don't smoke, agreed? I'm not allowing for any social smoking. Sometimes I quit. They either smoke or they don't smoke, agreed? Definitive. 2 possibilities, success or failure, only 2. Otherwise, it doesn't qualify. Third, the probability of success remains the same in all of these trials. So, in all of these trials, like A, B, C, D, or E, they all have the same probability of smoking, don't they? Which is 0.3. unchanged. So these qualifications are met, then we are entitled to do the analysis that I've just done. So now let's do it a little bit more slowly. Turn the page, and we're going to have some notation. In the green box, notation for binomial probability distribution. Small p, that's the probability of success in the background population from which you took your trial from. So your trial group, in our case 5, came from a background population, and the probability of success in that background population was known. It was 30%. So you have to know the probability of success for each randomly chosen person. That's the background population. Q is the probability of a failure. Okay? Now, N denotes the number of trials. In this case, I took 5 persons, 5 people. Each one of those people is called a trial, okay? I trialed this person, do you smoke? I trialed the next one, do you smoke? I trialed the next one, do you smoke? When I got through 5 people, that was my completion point. X denotes the number of successes that I'm looking for. In this trial of size 5, how many successes was I looking for? 2. Okay. Now, small p denotes the probability of success in one of the n trials. Small q denotes the probability of failure in any one of the n trials. If you pick any one of these people, A, B, C, D, or E, what's their probability of smoking? What's their probability of not smoking? That's their Q, agreed? Now, capital P of X denotes the probability of getting exactly n successes among the n trials. So here I'm looking for the probability of 2 successes in my group of 5. Now, how would my calculation change if I was looking for 3 successes? For 3 successes. So then I would want to know how many groups of 3 I could get out of my 5. And if I was looking for 3 successes, then there would be 3 30%, wouldn't they? So I would have p to what power? 3. And there would be 2 failures. And that would be p of 3. So now how would p of 4 occur? How many groups of 4 can I get from my 5? And then each one of those trials would have 0.3 to the 4th power and q to the 1 power. Now what's the probability of getting a trial of 5 and having 5 smokers? So you see this generalized formula, P of X equals C n of X, P of X to the n plus X, holds for all values of X from 0 up to n. From 0 up to n. Why from 0 up to n? Because n is the size of your trial. And you can have either 0 successes or total success. And X designates the number of successes. So X can be 0, no successes. Or 1 success. Or 5 successes. Now, if you satisfy those stipulations, then you can apply the formula for binomial probability calculation. That formula is at the bottom of 235. P of X, that is X successes in a trial of size n, is C n x. They call n factorial over n minus x, x factorial. It's another way of writing C n x. Times P of X, Q to the n minus x, where n is the number of trials. X is the number of successes among the n trials. P is the probability of success in any one of the trials, and Q is the probability of failure in any one of the 1 trials. Now, we're going to lead you into the validity of this formula by having you work a homework problem. So let's go to page 240. Same as my age. Page 240, and look at problem 13. Now we're going to answer this one assuming we don't know anything about the probability distribution formula. We're just going to reason it out. Multiple choice questions on the SAT test now have 5 possible answers. A, B, C, D, or E. One of these which is true. Okay? Now, if you close your eyes and drop your finger down on A, B, C, D, or E, what's your probability of success? 1/5, agreed? 0.2. What's your probability of failure? 4 out of 5, 0.8, agreed? So this is true on all the questions, is it not? If you guess randomly? So it's the background population, and it's a valid P, and it doesn't change for any one of the 3 questions, because you're doing them randomly. So P is fixed at 0.2, Q is fixed at 0.8, agreed? Now, we want to know the probability that the first 2 guesses are wrong, and the third is correct. So we know how to calculate probability. It's probability of A times the probability of B times the probability of C. So that means we have WWC. So now what's the probability of W? 0.8. Times the second W, another 0.8, agreed? Times the C, a 0.2. So what's the probability of getting a 0.8, 0.8, 0.2? So that number comes out to be what? 0.128? Good. Okay, now, I'm gonna ask a more general question. What's the probability of getting 2 wrong and 1 correct, no matter which one of the 3 is the correct one? So what are all the possibilities that you can have for getting 1 correct answer? You can have WWC, WCW, or CWW. Are there any others? Okay? Those are the only arrangements that yield 1 correct and 2 wrong answers. The first answer is wrong, the second answer is wrong, the third one's right. The first answer is wrong, the second answer is right, the third one's wrong. First one's right, the last 2 are wrong. Now, what's the probability of this occurring? 0.128. What's the probability of this occurring? 0.128. What's the probability of this occurring? So what's the probability of this, or this, or this occurring? Add them up. What? 0.384. So is this a binomial distribution? Does it fulfill those strict conditions? 1, let's go back to the page of
Either
strict,
one, right or wrong, right?
right or wrong. Let's go back to the page of strict conditions. Check them off one by one. So let's go back to 233. Does the procedure have a fixed number of trials?
Yes,
How many are there?
3.
3 trials. The trials are independent. Is your guess on the second question free from your guess on the first question? No overlap, agreed? 3, each trial must have success or failure. Is that true?
Yes.
And each success probability remains the same in any one of the trials. Your probability of success is the same in each of the 3 questions, agreed? Good. That means that this calculation can be done using the binomial distribution formula. The probability of x is C n x, p to the x, q to the n minus x. Let's make our parameter list. N equals what? C3, X equals number of successes, 1. P equals
One.
probability of success on any one question. What's the probability of success? 0.2.
Oh, okay.
And Q equals
Okay.
0.8. That means the calculation is C31 times 0.2 to the x power, which is 1, times 0.8 to the n minus x, which is 2. So what is C31? C31 is 3. And what is 0.2 to the 1 power? And what is 0.8? And the answer is 384. So we got the same answer by blind logic as yielded by the formula. So we're going to try a harder one, number 14. A psychology test consists of multiple choice, each having 4 possible answers, of which is correct. Use the multiplication rule to find the probability that the first 2 guesses are wrong and the last 4 guesses are correct. Okay? So what's the probability of success? Number 14. What's the probability of success? 1/4, 0.25. Agreed? What's the probability of failure? 0.75. So now, what's the probability of WWCCCC? So the probability of WWCCC equals 0.25, 0.25, 0.75, 0.75, 0.75. Which is equal to? No, it has to be less than any one of them. What is it again? One more time?
0.026.
0.02? 0.026. Maybe I misheard you wrong, I do apologize.
Oh, no, she.
Yeah. No, I was just wrong.
Why is it a higher probability to be
Again,
correct than wrong?
I know, I was not.
You have WW, you have 25, 25, 75, 75, 75. Is that switch?
because I got my head up my armpit.
Did I multiply it wrong?
Confused.
No, you're not confused, I'm confused. I'm glad you're here.
Confusion.
Okay. And this calculation becomes,
Were you doing it too?
Yeah.
0.0088.
if that's all the decimal places I can get, I'll take them. Okay, now, if I want to know the probability of any 3 correct answers, out of 5. Now, the 3 correct answers don't have to be the last 3, they can be any of the 5, agreed? So we need all rearrangements of WWCCC, all rearrangements. So can everybody make all possible rearrangements of WWCCC on paper? I'll make mine, you make yours. Aye. now. C, W, W, C, C. C, W, C, W, C. C, W, C, C, W. Okay. Now, I have C, C, W. C, C. C, 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 W, C. C, 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 W. Something went south.
Supposed to be two W's, correct?
Let's take this one over again. So now I have C, W, W, C, 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 W, C, W, C, C, W, C, C, W. Okay, now I have, C, C, W, W, C, 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 W, C, W, C, C, W, W, C. So now I have C, 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 W, W. I think I did it. I think I did it. Okay. 4, 7, 8, 11, 14.
You have repeats.
I'm freaky?
You have, you have a repeat.
Yes.
The last one of the second column and the,
And you have CW, CW, right beside each
Okay, you do it.
oh,
How many did you get?
other. Not that many.
I got 7.
Okay, well, it's easy to calculate because this is C5, 2. Which is 5 times 4 over 2, which is 10. So we should get 10, so I clearly have some duplicates. Yeah, these three are, this is duplicated. I did this one twice. Okay. So I have 4, 7, 10, 11, and I only have one duplicated now.
It's the.
Yeah, and this one is wrong. Okay, so I think my list is reasonable now. Now, which is the easier way to count these? By writing them all out or realizing you're taking C5 too? And is it true that that's all we're doing? We're taking C5 too, agreed? So that's where the C in X comes from. You can write them all out if you want to, or you can just take C in X. Now, what's the probability of this? We calculated, it's known. What's the probability of this one? Go ahead and calculate it or recognize it's the same, isn't it? Because it's the same 5 numbers, just in different order. Is not the probability of each one of those the same? And is not the probability of each one of those p to the x, q to the n minus x? In other words, p squared, q cubed. Or p cubed, 3 successes. P cubed, q squared, true? Every one of them? 3 C's and 2 W's. So every one of them is equal to P, P, Q, Q, Q. Aye, wrong. Every one of them is equal to P, 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 Q, Q. P, 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 Q, Q. Every one of them has a probability of that, which is P squared, Q, Q, which is P to the x, Q to the n minus x. So every one of those groupings has a probability of P to the x, Q to the n minus x, and this is how many groupings there are. So once again, we come to the binomial distribution equation. The probability of x out of n is equal to c in x, p to the x, q to the n minus x. So the purpose of these two problems was to convince you of the validity of this equation. To convince you of the validity of this equation. Now that that's been done, all we're going to do is go about using it. So on your textbook, page 241, number 21. N equals 12, x equals 10, p equals 3/4. So we're going to use this equation for these parameters. N equals 12, x equals 10. And p equals 0.75. So that means that p of x is equal to c 12, 10 times 0.75 to the 10th power times 0.25 squared. So let's please do the calculation. What is it?
12323.
0.2323, all in favor? Nice going. 0.2323. Now that you know how to do that, I'm going to go to the complete table. The complete table for n equals 5. N equals 5. So I want to have this is a probability distribution now. And this is n equals 5, and I'm going to say that p is equal to 0.3 and q is equal to 0.7. And I want a complete probability distribution. Now when n equals 5, what are the different number of successes that I can have? I can have no successes, agreed? Or I can have one success, or n equals 6. Oh. N equals 6. No, n equals 5. Okay, got it straight now. Or 2 successes, or 3 successes, or 4 successes, or 5 successes. Those are the number of successes that I can have, agreed? Now each one of those has its own probability. The probability of x here is given as, probability of x is always c n x, p to the x, q to the n minus x. So what is the probability of 0? The probability of 0 is equal to c to the 5, 0, 0.3 to the 0, and 0.7 to the 5. So please calculate that probability. C05 is 1, isn't it? C50 is 1?
Yes.
So it's 1, and 3 to the 0 is also 1, but 0.7 to the 5th power, I'm going to leave up to you. So Freddie, Stephanie, what we're doing now is a complete probability distribution for all possible values of x. So what does this one come out to be? 0.5 to 0.7 to the 5th power is?
0.16807.
0.16807. Okay, now, don't anybody do anything because I'm just going to write down the formulas for the rest of them. P of 1 equals C 5 1, 0.3 to the 1 times 0.7 to the 4th. And P of 2 equals C 5 2 times 0.3 squared times 0.7 cubed. And P of 3 equals C 5 3, 0.33, 0.7 squared. And P of 4 equals C 5 4, 0.3 to the 4th, 0.7 to the 1st. And P of 5 equals C 5 5, 0.3 to the 5th, 0.7 to the 0. Okay, now, Hannah, you do this one. Casey, you do this one. Stephanie, you do this one. Tony, you do this one. Kaylee, you do this one. And Freddie, you supervise. Make sure they get them all right. So we're distributing the work. So Kaylee, somebody tell me when they get their answer.
I have 2.
You have 2, that's the that's the blue one, Drew?
Yes.
So your number is?
0.3087.
Okay, we're waiting for more input now. Tell me which one you got.
1.
The red one, right?
Yep.
Your number is?
0.36015.
Okay, let's get some more input.
I have numbers
Just a
for
second, let
problems.
me get this correction. Okay, and you have which one?
Probability of the 3,
Of the 3, and your answer is?
0.1323.
0. What?
1323.
Good, only 2 more to go.
So for 4, I have 0.02835.
1 to go is exciting now. 0.6, 0.76, doesn't look good, looks bad. See what 5. Tony, check that one more time, it looks too low.
Are we doing it right now?
Yes, right, it looks too low.
Is it, wait, is it times point three into the fifth, or is it just times
This one is 0.3 to the fourth power, times 0.7 to the first power.
So then I have, numbers right?
Just a second, oh, you have the last one?
Yeah.
What's your last one?
I have 0.00170. I said there's something really, really wrong that I got the same answer twice. I got the same answer as well.
Good, okay, now, let's do a little bit of belief. Is this a discrete probability distribution? In other words, have we covered all of the possible values that X can take in 5 trials, agreed? Now, if this is a discrete probability distribution, then these probabilities have to add up to what famous number? 1. 0.62, 0.95, 1. So indeed, this is a discrete probability distribution because the outcome must be in one of these buckets. The value of X is either going to be 0, 1, 2, 3, 4, or 5. No other values allowed. And these probabilities are associated with it. So you see how you use the formula for a discrete probability distribution to complete the table of all possible probabilities for any member in this data set. And they all have to add up to 1. So now I'm going to incur your wrath a little bit perhaps, because in the back of your book, I'd like you to find table A1. Table A1. Can someone find a page for it, make it easy for everybody else?
780.
780. Now in this page, in this, actually
79 is where.
79, okay? Now, I would like you to find the entry into this table for our value of n. What's our value of n? I believe our value of n is 5. I believe it says 5 up there, doesn't it?
Yes.
So our value of n is 5. Now, now we want to find the column for our value of p. What's our value of p? 0.3. Now so you see the entries for x? So can you use this table to tell me whether our 0.168 is correct?
Yes.
You find 0.168? Is our 0.36 correct?
Yes.
0.309?
Yes.
So now, could you have used this table instead of the calculations? No, because I wanted you to do the calculations. Because that's where the table comes from, agreed? So now you know where the table comes from. So you have a value of n, and you have entries here for all possible values of x, 0, 1, 2, 3, 4, 5, and then spread out across the page are the different values of p in the background population. So now let's go back to page 241. And here are the instructions for problem number 18. It says use the table for this one number, n equals 14, x equals 4, and p equals 0.6. Page 241, number 18. Page 241, number 18. So work with each other, see if you find consensus. N equals 14. Oh, is it even on the table? I guess it is. Yeah, 14, and x equals 4, and p is equal to 0.6. I've got my number. Keeping it a secret.
Friends don't make secrets.
We're not friends.
Touche.
Oh, burn.
Was that a low blow?
Well, you knew it as soon as I kept it a secret, didn't you? I mean, you didn't have to say that. Hannah, your number is?
.014.
All in favor, .014. Kaylee?
I was still doing
No, it's just a table lookup.
it. Oh, okay.
Table lookup. Point says, these guys aren't that fast.
Definitely not.
No.
Trust me.
N equals 14. N equals 14. X equals 4. And P equals 0.6. 0.014, right?
Oh, yes.
Good.
Got it, okay.
Okay, now just to wear you down, number 16. N equals 5, X equals 1, P equals 0.95, that's not in the table. So problems, 95 is in the table. 5, 1. 5, 1, and 0.95. Tony, your answer is?
0 plus.
0 plus, which means a smidgen. Too small to write. 0 plus. Good. Now, let's go back to page 241, please. And, in the right-hand column, we have a probability distribution. My first question, is it really a probability distribution? All in favor? Do they add up to 1? You're using 2 hands and they're beating you.
Yes.
It is a valid probability distribution. So let's continue. Let's read the blueprint to the left of it, using computer results. So Tony, could you read that blue paragraph, please?
In exercises 25 through 28, refer to the accompanying Excel display. When blood donors were randomly selected, 45% of them had blood that is group O, based on data from the Greater New York Blood Program.
Okay, may I interject? So what is 45% going to be? What number?
0.45.
In our selection, N, X, P, and Q, which one?
Wait,
N?
N, X, P, or Q?
P,
No, not,
It's P.
P,
It's P.
P, right? It's a background percentage. It's a background percentage. What's Q?
0.55.
Good. Please continue.
The display shows the probabilities obtained by entering the values of N equals 5 and P equals 0.45.
Okay, now, 25. I just want the answer. Find the probability that at least one of the 5 donors has group O blood, at least one. There's an easy way and a hard way. I hope you do it the easy way. Well, you're not gonna find it in the table, you don't need to, because this table has now been filled out. These numbers in column B came from the table. They came from the table. Table is established. The probability column is established. And then you got it the fast way, they're doing it the slow way. So Stephanie and Casey, are you adding up 1, 2, 3, 4, and 5? At least one. Tony is subtracting the first one from 1. Back to her approach. Uh-huh. She's that way, you know. In other words, that column is already these numbers. They've already looked them up and written them for you. Okay, so what's the answer for 25? Anybody?
94967.
Everybody got that? So you know how to get at least one? You add up the probabilities that belong to 1, 2, 3, 4, 5. You add them up. Or else you just subtract the first entry from 0, from 1. Because they all have to add to the backdoor approach. Okay, let me ask you this, Kaylee. If you added up the probabilities for x equals 1 to x equals 2 to x equals 3, x equals 4, x equals 5, if you added those up, can you tell me what you get? Okay, let's pretend. Write it down. What do you get? 0.9?
0.94 or something.
Okay, good. Now, Kaylee, if you subtract the first probability, 0.05033 from 1, tell me what you get. Same number, right? Isn't it the same calculation? It's the same calculation, front door, back door. Okay. Number 26, at least 3, at least 3, at least 3. So this is equal work either way, agreed? So what numbers are you going to work with?
3, 4, 5, and 6.
There's no 6. Oh, okay, in the X column, 3, 4, and 5. No, you see, the first column is meaningless. It shouldn't even be there. Only the bold print matters.
That's just
Only the bold print matters. So we go to 3 successes. 0.27, 0.11, 0.01.
0.40687.
Agreement. Okay, people working on it.
So it would just be 1 minus the 3? Like.
You said 0.4067.
Hannah, tell them how you got it.
Added 3, 4, and 5 successes together.
What particular numbers did you add?
Oh,
0.2.
0.27565, 0.11277, 0.018445.
It says
At least 3.
Okay.
Yeah.
Next question. Find the probability that all of the 5 donors have group O blood. All of the 5 donors. No calculator. No.
0.018445.
Thank you, thank you.
What?
Number 5,
Oh, got it.
Oh.
all 5 successes.
Give me strength. All right, now find the probability that at most 2, say it louder so they can agree.
0.59614.
Agreed, yes. People are on board. Okay, time for our go home problem.
Oh.
So we're going to work with number 31, go home. And table is permitted, or the serious student, of course, will use the formula, but table lookup is permitted. Okay, who's gonna get us out of here early?
Oh, yeah.
Motivation. See those pages burn, that smoke's coming out. Number 31, you'll read the answer in the back of the book? That's not allowed. That's not allowed, I'll do that. Another problem. So at least 12. I don't know the answer. You have to get consensus with your classmates.
Yes, I'm with you.
1001,
Go home.
is that right?
He just told us to go home, so I'm going to assume so.
Oh, I do that, but that's
Okay, I'm still collecting homework at your discretion
Oh.
for test 1 homework. Test 2 is a week from tonight, no class Saturday, but workshop Saturday 2 to 4. And we do have class Thursday in 48 hours.
So it's up to 1, or.
And the assignment that was given to you, so it's page 229 and page 239, some selected problems.
Do you do the homework at the A4, like 1?
Yes.
A1 through A4?
Right, that's what we're talking about.
I have notes.
And A1 and A2 are marked in the appropriate pages, like this.
Oh, okay.
Okay, good to go. Very well organized. Is that the second time you did the homework? Did you recopy it?
No,
You did that for the first time?
yeah.
Ah,
You did better than me.
I didn't say anything.
Yeah, just give you
I
what.
didn't say anything.
Sorry,
Actions
I-
speak louder.
Excuse me, ma'am?
Actions speak louder, did you know that? Got nothing?
I'm a quiet person.
Sorry about number 33, by the way, we checked out homework Saturday and I kind of forgot everything for obvious reasons, so,
No big deal.
my mistake.
No big deal. Gracias, senor.
Can't really see very well, that's my bad.
I'll take care of it when I need it.
Maybe when it's over, I'll bring it around.
If I'm good, right? Nice coat, dude.
$2.
Thrift stores took away.
Sky Plaza. My wife got it for me. She goes there all the time. Well, about once a week. She goes there to see what they got. She saw it, like, I get this for $2. Again.
It's not that often you can find your size, is it?
It's a big enough.
Yes, A6.
No.
No, A7.
A7.
A6 should be
The
done,
new
we just
handout.
haven't checked it yet.
Okay.
You didn't check our 6 yet? Oh, thank you, my omission. We could have stayed another 10 minutes and done work. Nice.
That's okay, half the class is gone. Nope, nope, nope.
Totally overlooked it.
And the rest of us are ready to go.
Yeah, I think we did enough. Only way to keep it open is put a table in front of it. That joke was totally successful, to put that joke there, you called that one right on. He went for it, it was good. Some people would have gotten uptight. You knew him.
If you catch them in a good mood, it's fine. If you don't play jokes on people.
I
You're not in a
have
good
my
mood.
notes mixed in with my homework. Can I bring it back on Thursday?
No, we don't accept anybody except Hannah. We accepted it from Hannah, so we will accept it this time, but please try to separate them from future grading. It's difficult, if you
Well,
can.
That's,
Yeah.
Mine's in there too.
Well, I mean,
But
I
these
just-
next ones I've started separating.
Separate notebook.
yeah, I bought a separate notebook because I was like, I can't.
Okay, if it's a hardship for you, then don't separate them, leave them together.
No,
But
I
from
mean,
now
I can
on,
separate them, I just.
no, don't separate them now, just hand it all in. And from going forward, if you could separate them, it helps. But if you want to not separate them, that's okay, I'll work with it. I cross to bear.
They're now separated for next time for me.
Alright.
Thursday.
Go then.
We'll have fun and learn chief with homework. It's always fun.
Life is good.